Hello everyone, and first of all, a warm welcome on behalf of the EMAG Group here live from our studio in Eislingen, Germany. We are very pleased that you have decided to join our webinar today on the topic of gear machining. But before we start straight through, we are going to introduce ourselves briefly. My name is Jörg Lohmann. I am head of technology and sales from the business unit Gear Machining Soft. I can look back on a career of more than 20 years into gear business, and I am here together with my colleague, with Alexander Moorhardt from the business unit Gear Hobbing Hard, and he can even look back on a longer career. He is in the gear business since 35 years or even more.
Yeah, also hello from my side.
Well, before we start straight through with the topic, there is still an important organizational point. Kind attendees, this is an appeal to you. Please feel invited to send us your questions, whatever question you may have. There are two possible ways to send us those through. Either you use the public method by means of the chat, or you send them through simply through the questions function that we have here in this webinar. So it will be non-public. It will appear directly here in my screen. And during the webinar, we will try to reply to those questions. In case we should not be able, due to time reasons or so, we will of course reply to those after the seminar via email. Right, okay, so let's get started. What is the content of today's webinar? Gear hobbing, power skiving, gear shaping, skive hobbing, generating grinding, and of course also profile grinding, which is the right machining process for my application. And the targets of our webinar are the following ones. We are going to give you an overview of a variety of different gear machining processes. Then we are going to show you possible process chains on components with gears, and we present practical applications on EMAG machines that we have already realized in the past for our customers. The business unit I come from is placed in Villingen-Schwenningen, Black Forest area. Here the focus is on horizontal gear hobbing machines up to module 4, diameter 200 millimeter. The technologies are hobbing, skiving, that means skive hobbing, worm milling, and also power skiving processes. And Alex, I kindly invite you to introduce your business unit as well.
Our business unit EMAGLLC is located in Anzola. This is in Italy, close to Bologna. And our products are vertical and horizontal hobbing machines, vertical and horizontal profile cutting machines, shaping machines, shaving machines for the automotive industry, horizontal profile grinding machines with different application, and vertical generating and profile grinding machines. The maximum diameter we can produce is up to 500 millimeter. Right.
Let's come to the classification of the manufacturing processes of gear production. There is a specific breakdown according to the DIN standard. It's the DIN 8589-6 that classifies these processes, and here is the overview. We have machining processes in so-called involute coupling. We are going to talk about this a little bit later on more in detail. That means, for example, hobbing, shaping, and skiving. Then we have the machining processes in profile coupling. This is profile milling or single index milling, for instance, or broaching. Then we have chipless processes such as rolling, casting, or sintering. And last but not least, of course, there are also the fine machining processes such as generating grinding, profile grinding, or gear honing. So what is the meaning of a generating process? I'm trying to explain this to you a little bit more in detail. On the left side of this slide, we have an overview on the different processes. There's shaping, hobbing, and power skiving shown. And on the left side, you can also see this, well, let's call it a basic rack. And the basic principle of this generating method is explained on the right side of the slide. Let's take a look here on this basic rack. Let's assume we would conduct a cut into the plane of this slide here. So we have a gear, this is shown in gray color, and we have this blue colored basic rack, and now we conduct a cut. What will happen? We will, of course, have the negative shape of this basic rack in our gear. If we now were to rotate the gear slightly and simultaneously shift also our basic rack, and we were then to execute another cut, we would, of course, leave the pattern once again. And by means of this, generating, by means of this coupling of the two, we make sure that these patterns overlap in a certain manner. And this is how it works to realize an involute tooth shape by means of a straight basic rack profile. Of course, this leads systematically to certain deviations. This is the so-called profile deviations, one of the systematic deviations that are known from the gear hobbing process, for instance. Here on the lower side of the slide, you can still see a realistic simulation of a steering pinion. It's a tooth gap from a steering pinion, and you can see how this tooth follows a trochoidal path into the tooth gap and out again. This will still be overlapped by the axial feed rate. That is actually a movement, a linear movement into the plane of the slide. Which process is the right one to choose? First and foremost, there is, of course, the feasibility. Here on the left side of the slide, we can see a nice picture from Ruben Bauer, who has written his dissertation at the IWO Fraunhofer in Chemnitz. And he has made a very nice example. You can see in gray color this workpiece. It is a kind of spline, and it has an adjacent shoulder. And here we see the three different or potential green machining processes: gear hobbing, gear shaping, and power skiving. And there is one significant difference. In gear hobbing, we have a hob and a gear, and they interact with an x-crosses angle that is round about 90 degrees, so we have crossed axes. And as you can see here easily, we would have interference with the adjacent shoulder if we were to hob this workpiece. So this will not work, of course, but there is an alternative process available. This is gear shaping or also power skiving. With gear shaping, we have the shortest over travel of the tool. That means, we just need some tenth of a millimeter in order to make the tool exit, make it get out of the gear we are machining. And this is enough, so we can machine this part here with this adjacent shoulder due to the reason that the axis of tool and workpiece are actually aligned to each other. They are parallel. And then there is the power skiving. This is a little bit somewhat in between with regards to the over travel of the tool, because here we have the workpiece symmetry axis, and this is inclined with an angle of approximately 20 degrees. This is necessary in order to make the process work. This is where actually the cutting speed comes from. This is the basic kinematics of power skiving. And here also a certain over travel is required, but way less in comparison to the gear hobbing process. On the right side, we have still from the dissertation of Dr. Ruben Bauer a categorization chart. We have the productivity and the flexibility on the two axes of this diagram. And we see on the left side the broaching process. Broaching is considered to be not very flexible. Why? Because simply every broaching needle is dedicated to each individual internal gear that is going to be broached. So there is not much flexibility, of course, but it is considerably productive since only one stroke is required in order to finalize the internal spline. Then we have hobbing. This is very productive and flexible at the same time. I 100% agree with that, because hobbing gives us the flexibility to use one basic rack, that means one hob profile, to hob any number of teeth, as long as there is no profile modification required in the hob. That means that makes this process extremely flexible or versatile, and also productive, since it is a continuous machining process. Then comes power skiving here underneath hobbing on the right side. It is here considered to be quite flexible and also productive. I think one can argue a little bit about that, because by the one hand, it is flexible. Yes, we can machine different workpieces, even workpieces with adjacent shoulder. But the disadvantage is that we need an individual tool for each individual workpiece that we machine, each gear geometry?
Yeah, I think the flexibility in this process means that we are able to do external and internal gears. Maybe this is the point why the flexibility is higher as it is with the hobbing process, and I think this is coming out of this matter. So it makes sense that this is located here more flexible as it is with the hobbing process.
This is definitely true. Thanks, Alex. Yes, of course, we can do internal splines, external splines, workpieces where we have adjacent shoulders. So this is probably why they decided at that time to determine this to be a flexible process. And last but not least, of course, there is also the shaping process in this chart. It's considered to be flexible but less productive. Why? Simply because of its kinematics. The shaping process is a process that is of non-continuous character. That means we have linear strokes that conduct the cutting movement. And due to the reason that it is simply not continuous, it is less productive. Which are the accuracy classes on the gears that one can achieve with those processes, and which is the surface finish as far as the roughness values RZ are concerned? Here we have prepared a nice overview for you. It shows you the different processes here in the first line. Underneath, in the second line, we can see the corresponding accuracy classes according to the ISO standard 1328-1. And then in the middle of the slide, we have the hardening process, and then we come down to the hard finishing processes. Let's make one example here. The second column from the left is soft finish hobbing. We can achieve an accuracy class, well, with a good tool, make 3A or even 4A accuracy. With a good blank and a good machine, of course, and work holding fixture, we can achieve maybe class 6 to 7 and a surface finish on the flank of RZ 2.5, corresponding to an RA value of approximately 0.5 millimeter. Then comes heat treatment. And Alex, what would you say, what is achievable when it comes to the hard fine machining processes?
Yeah, with generating grinding, you come down up to class 5, and with profile grinding, it's a little bit better, up to the class 3. This, of course, has always to do, as you mentioned before, with the tools which we are using, and also with the how good is the income quality, is the quality of the clamping fixture. So this has also an influence on the achievable quality you get out at the end. As better as these clamping fixtures and the incoming quality is, as better is the final quality at the end, of course. And also with the surfaces, depends which kind of tools you are using, which kind of roughness you can achieve at the end.
Alex, one question. Besides the conventional method of generating grinding, I think there is also Polish grinding.
Yes.
Would you consider Polish grinding to be the new industrial standard for the OEM and Tier 1 business? What would you say?
No, I don't think so that this is the standard. The reason is when you are using Polish grinding, you must do a rough and a finishing pass, and then jumping in a different area of the grinding wheel and do the polishing pass, and this took more time. So also the costs are higher. So I think in some application it makes sense to do this, but in other application it makes no sense. And so there is maybe some balance between these two kind of processes. Maybe an alternative to this is the fine grinding, where we do a roughing and a finishing pass on two different crane size of the grinding wheel himself. So I think this is something in between.
Right. Okay. Understood. Thank you. So let's come back to the topic of the process chains. Here, this chart shows that there are many different viable ways to machine a gear. On the left side, we see blank. This can be a forged part. It can be, well, a slack. It can be maybe turned from the bar whatsoever. And the question is, how can we come to the final status of the gear? And I would say when it comes to the determination of the process chain, the properties of the final product determine how the process chain should look like. Here are some viable ways. Let's start from the right side of the chart. We see powder metallurgical processes, for example, sintering. This process is a very good solution when it comes to extremely complex geometries on gears. In case you have a gear where you have blind holes, any slots or cams or so forth, if it's really a complex geometry, then powder metallurgical processes can really make sense. There is, of course, the disadvantage that still today, powder metallurgical gears usually are not yet on the same level like conventionally produced gears as far as their mechanical properties such as tensile strength and so forth is concerned. An alternative to this is the precision forging process. I always think about the straight bevel gears, for example, in a differential gearbox from a passenger car. These gears, for example, are usually precision forged so that there is actually no chip removing process as far as tooth machining is concerned. And then comes, of course, here in red and green color, the two typical paths that we know from gear machining. So first of all, we start, for example, from a slag. Then we have machining of the wheel body. We talk about rotating workpieces usually, so turning is usually the preferred method. This could be made, for example, on an EMAG VL3 Duo, Op10, Op20 turning. Then comes green machining of the gear. This could be, for example, hobbing. Now we follow along the green path. It could be finish gear hobbing. Again, if we use an appropriate hob in good accuracy, good blank, good work holding fixture, good machine, and we apply, for instance, a two-cut strategy, we may achieve a DIN quality class 7, and the workpiece will either still be hardened or be ready immediately for being assembled. And the red path foresees the heat treatment in between, and afterwards we have hard fine machining, such as, for instance, generating, grinding, and then we will end up, of course, in a way higher accuracy as far as geometry, gear geometry and surface roughness is concerned. How can such a process look like when it comes to pre-hobbing, rough hobbing, before gear grinding? Here we see an application on a Köpfer 160 gear hobbing machine, horizontal style. On the right side, we have the automation cell. On the left side, there's the work area. And here now the movie shows the so-called servo distributor. This consists of two additional auxiliary axes and C-controlled axes that take care of the workpiece handling. So these blanks here roll down by gravity on such a chute magazine. And once the workpieces have been finished, they will be deposited underneath on the conveyor belt. Now we see the process. This is now a tungsten carbide hob, shank type execution, diameter 50 millimeter, 17 gashes, 2 starts, dry hobbing, Alcrona coated, single cut strategy. On the left side, you see the deburring disc coming from the lower side in order to remove the burr on the face side of the gear. And here again, the finished workpieces deposited. This is now pre-hobbing before grinding. Gear accuracy class 9 is sufficient in this case. And the cycle time here is less than 10 seconds. So it's quite quick. Right. Then there are, of course, also larger, bigger machines within the EMAG Group and also from other business areas such as industrial or agriculture business. I think, Alex, you have a lot to tell about these applications, right?
So we have bigger horizontal machine. All these machine has direct-driven table and direct-driven hob head. And these machines are available in different axial travel, 1.5 meter, 2 meter, or 3 meter for the CLC to 60H. And on this machine, you can cut long shafts, warm gears, normal gears, of course. So these are also good machines for job shop company who has a big variation in their parts. But also in the truck industry or in the defense industry, there are a lot of long shafts where the two gears at the end must be aligned to each other. This is here the perfect machine for this because you can do this you can cut on both sides in one clamping and have an inductive sensor, a retractable inductive sensor, which can be swiveled out to find here the right position to each gears. Why does it works on these machines? In the right picture on the right side, you can see an automatic steady rest. So this is a 3-point steady rest, which can be moved automatically on the OD of the part and can be positioned in the machine wherever a gear is located. So here the setup time is very small. This part will be clamped between a face driver and the center on the tailstock side. And then with the steady rest in the right position, you can cut all the parts, all the gears along this part. And there is a possibility to have 4 different gears on a shaft, which can be produced in one setup. Also on the left picture, you can see assembly of a tool arbor. Here we have 3 different hobs on the machine. This is a module 4 and module 2 hob. And in between, there is a chamfer cut unit where we can cut, where we can produce a chamfer on the module 4 part only from one side. It depends here on the part we can use. So here, the maximum length between center is a part of 3.2 meter on this machine, but also there is a table through bore with 80 millimeter where you can put longer parts through this table bore and then cut the part on one side, move it out, turn it around, and then put it again. Also, these machines are available with a milling cutter head for cutting wands, for example. And loading normally is here with a robot. And we have also a nice chain storage where also different lengths and different size of workpieces can be stored during the process.
So I would still come back to the topic of the process chain. Here is, for example, one well-known workpiece. It's a steering pinion from a passenger car. And there's one typical process chain. It consists of turning op 1020, could be done, for instance, on a VL2 or 2 VL2s that are interlinked to each other. Then comes the hobbing process. We achieve quality class 8 as per ISO 1328. Then comes the hardening process. During the hardening process, distortions will appear. That means we will lose 1 or 2 classes depending on how we harden the workpiece. There are, of course, also different behaviors depending on the different hardening methods that are available. Steering pinions usually are either case hardened or induction hardened. Then we have a loss of 1 or 2 classes, and now we have the possibility to recover. That means we can use exactly the same gear hobbing machine once again and can do skive hobbing or simply skiving with the same machine by means of a tungsten carbide hob, and then we will come back to an accuracy class 7. Here are the inspection charts of such a workpiece. On the left side, we see the quality class 8. And here in the middle of the chart, we see what happens after hardening. And you can see that there is a strong distortion with regards to the lead direction of the part. It's even more than 30 microns. And on the right side, you see what happens after the skiving process. So we can come back and recover and achieve an accuracy class DIN 7 on the hardened workpiece. Well, there's still to add, if we know that we have a distortion of 30 microns in the lead, we would, of course, already pre-compensate this in the green hobbing stage so that we make sure that we have a nice uniform and constant stock allowance along the whole lead of the workpiece. Another workpiece that can be pre-hobbed and skived on our machines is a rotor shaft from an E-drive. We see here a movie from such a workpiece. There are different kind of rotor shafts. We will soon offer also a webinar for machining of rotor shafts. Here we have the K160 in long bed execution. Long bed means simply the machine has been stretched in axial direction. So we have a longer axial hob stroke. It's now 480 millimeters with this machine. And we can machine parts up to 600 millimeter in length. And here you see it's a roughing process. You can see that we have considerable feet scallop marks on the gear, but this is also permitted because it's just pre-hobbing. And now here the distributor deposits the workpieces underneath the chain magazine on this conveyor belt. So this was pre-hobbing. Now let's switch over to the skiving process. It's the same machine type with a different automation. Here, the customer wanted us to prepare the machine with 2 chain conveyors, one coming from the front and one depositing the workpieces to the rear of the machine. Now we load the workpiece that already has existing teeth, of course. And now comes the auxiliary tool with the skiving probe and a free-blown nozzle. And we detect the already existing teeth, and by means of a reference signal, we can calculate and evaluate the C-axis offset that is required in order to make sure we find the tooth gap of the existing gear. Skiving can be made either wet or dry. There are advantages and disadvantages. Sometimes dry machining allows us to avoid or skip any washing operation. By the other hand, sometimes we have to reduce cutting speeds in order to avoid surfaces from burning. Right. Now let's come to another EMAG product. It is the HLC 150H, and this is our most versatile gear hobbing machine. It is not only a gear hobbing machine, it's actually also a worm milling and a power skiving machine. We can do hobbing applications, skiving applications, worm milling, worm skiving, that means single index milling by means of disc cutters. And we can also do hobbing of worms and moreover even power skiving of external gears. This is now external gears. In case we wanted to machine internal gears, we still have other products within the EMAG Group like the VSC 400 PS power skiving machine. But here now this is external gears and shafts. How is it possible to realize all this in one machine? This comes from a very innovative concept that I'm going to introduce to you now. Here on the right side, on the top, we still see a little, well, let's say an outlook into the future. We are right now developing the radial gear chamfering method for this machine as well, so that we can chamfer gears whenever it is required. So what is now the secret of this new concept? Well, on the left side, you see the conventional machine kinematics of a horizontal gear hobbing machine. How does it work? We have a direct-driven water-cooled hob head that drives the tool, and right underneath we have the Y-axis, the shifting axis, and this consists, of course, of a bolt screw spindle, the guideways, and this axis makes simply sure that independent on the axis independent on the hob head inclination, we will have the right direction for shifting of the hob. And after those axes comes the pivot point, that means the A-axis that swivels everything. On the right side, we have our new concept. It's an innovative design. We still have a direct-driven water-cooled hob head, of course, but instead of having immediately the Y-axis, the shifting axis underneath, the whole hob head is suspended from its pivot point. That means immediately comes the A-axis. That means we can swivel the hob head, and by means of a so-called physical Y-axis here in orange color, we can move the whole pivot point, or also called plunging cylinder, up and down. And this gives us a completely new degree of liberty. And this allows us to unify two important things. A long shifting range of 220 millimeter, and at the same time we can swivel the hob head on 180 degree. So we can machine any helical gear whatsoever. So we make benefit of this when it comes to machine worms and worm gears. Here we see three different applications. We have a worm that we will single index mill by means of disc cutters. Then in the middle comes the tangential hobbing method of multi-start worms. And then where the worm is, the worm gear will not be far. Of course, also various hobbing methods for worm gears. Let's start with the worm milling process. This is now the HLC 150H horizontal machine. Pretty similar design as shown already with the K160. We have a chute magazine, the worms roll down by gravity, distributor prepares the workpieces for the gantry loader, in this case a gantry loader with linear gripper up to workpieces with a weight of 10 kilograms and diameter 150 millimeter. And now you can see that we apply a special strategy. This is a 3-start worm. The first start is cut by conventional cutting. Now we switch for the second cut to climb cutting. And the third start will be cut again by means of conventional cutting. Why do we do this? Well, very simple. We can save time because in this manner we can avoid empty backstrokes. And this simply is another plus when it comes to productivity.
Can we also deburr these kind of worms on the machine?
Good question, Alex. Yes, we can. We even have developed a conversational software program for our HMI. That means if we so want, we can deburr the sharp edges for each start by means of the milling cutter. That means once we have cut them, we go back to the initial position and then remove the sharp edges.
Yeah. What is the maximum module you can cut on this machine for worms?
For worms, it's module 4.5. With 4.5, we still find considerably okay. But when it comes to hobbing, it's maximum module 3.5 approximately. Yeah.
Okay, we have, of course, in EMAGLLC bigger machines for milling worms up to module 12 with 500 much more. So we have two different possibilities. We have a CLC 260 HFR, which has a worm milling head on this machine. And also we have a vertical machine, also with the same worm milling head, but then 4-station ring loader, and we are able to cut also the keyways in the 90-degree position. So to have high productive machines for worms, also for bigger ones, that we can do this really in a short time and with the additional process on top.
Does that mean that you can mill the keyway even in the idle time?
Yes.
That's
100% in the idle time.
Yeah.
So this is a fantastic machine because you have both processes and can be sure that you have also a key milling in this. And also we can measure the keyway, of course, the size of the keyway in the machine.
Great. Okay. Here now let's come to the second application that we show. It's the tangential hobbing of multi-start worms. And here we have a relatively new patent that has been applied for last year. And this allows us to machine multi-start worms by means of a hobbing process. So it's not single index milling, it is hobbing. And we do this by using our axis arrangement of the HLC 150H. That means in this case, we move the hob head actually simply straight upwards. We move the hob along the circumference of this worm using a multi-start hob, and this has a very big technological advantage. The advantage is that in gear hobbing we usually have two kinds of systematic deviations, the feed scallop marks and the profile deviations. By using this method, we can make sure that the deviations will be, so to speak, washed away by themselves. So they will overlap or overroll, and that means the workpiece cleans itself up from these systematic deviations. In other words, we can use even a 3-start hob for a worm with 3 starts without any lack on pitch or other deviations. So this is a very innovative process that we have patented. And this, in this particular case, cuts down the cycle time to half in comparison what this customer did before. Where the worm is, the worm gear is not far. Let's take a look on our worm gear machining capabilities. Here we have the machine set up for bronze worm gears, still the gantry loader with linear gripper. And now you see this titanite coated hob. It's a shank type hob for hobbing this globoidal worm gear. And what we do here is simply radial plunging. So we plunge in with a radial feed rate that is non-continuous. That means it is digressive. And once we have achieved at final depth of the tooth, we will still allow 2 RPMs for dwelling in order to make sure we have the full depth on 360 degree of the gear. This is possible as long as the helix angle is smaller than approximately 11 degree. With steeper helix angles, like in this case here, we have to apply a different method. This is now the tangential hobbing method. Here we have a hob with a taper, and there is one disadvantage. It is, of course, slower, and you cannot shift this hob, but we have to apply it because if we were to plunge this workpiece, we would cut off material that we would still need later in order to achieve a good contact pattern. This is why we apply it. And here is now an alternative to this process. You see a cylindrical hob. We can shift this hob, and this is, well, we call it the high-performance hobbing method. And this hob allows us to plunge in even with high helix angles. Why? Because we realize that the tooth thickness by means of the machine kinematics. In other words, once we have achieved full depth, we make a shifting stroke along the y-axis in order to finalize one flank, and then we go back and finalize the other flank. So the tooth thickness is not created by the thickness of the tooth of the hob, but it comes from the kinematics. It's completely controlled, and this allows us to combine the advantages of plunge hobbing with workpieces with high helix angle. Also from EMAGLLC side, we have, of course, bigger machine up to 500 millimeter sure. with the same software option as here on the HLC 150C. So we can machine these kind of worm gears up to 500 millimeter, of course. Thanks. Power skiving on the HLC 150. What is a potential application for this? Here we see a drive shaft for a hydraulic pump, and these workpieces usually have at least 2, if not 3 gears. And you can see on the left side that there is a spline, according to DIN 5480, that cannot be hobbed because of the interference problem that I explained initially. And on the right side, you can see that the designer of this workpiece has already taken into account the fact that there is a certain sweep out for the hob required. So this can be hobbed. There is still another workpiece from this family. Here we have 2 splines on the right side. Those could be hobbed in one setup, for example, by using such a tandem hob as shown in the upper right corner of this slide. Or this may be, of course, also 2 bore-type hobs that have been assembled into one hob arbor assembly. And on the left side, we can go in a separate setup and then power skive the spline where we have the interference. How does this look like on the HLC? Here is a movie. This is a planetary gear that we cut for trial purposes, and you will see the power skiving process. Please be aware that we are using here cylindrical tools. That means we need an offset from among tool and workpiece symmetry axis, and we can realize this in order to give this tool its kinematic clearance angle that is required.
But when I look on this process, this is not so far away from the hobbing process or from the speed here.
No. I think, if we were to consider the net time, the contact time between tool and workpiece, then I trust it would be even more productive. But due to the fact that it is a non-continuous process, we have to apply multiple cuts, and this predominantly depends also on the tooth height. So there's a difference whether you have a full tooth or a stub tooth from a spline. Yeah. I think this is actually what makes the difference.
Yeah, genau.
Yeah. Okay. Yeah. Right. General industrial applications. I think, Alex, you have collected a lot of experience in this area, so I kindly invite you to tell us something about these applications.
Yeah, thanks. So also on the grinding side, we need very flexible machines. And the G375 is one of these flexible machines. When we stay here in the worm shafts, for example, which you can see in the middle of this slide, there are all the possibilities, all the standard profile forms we have as a standard in our HMI. So it's very easy to cut these kind of parts. But also hydraulic pumps, as you can see on the top, or a rotor pump, as you can see below, are possible to grind on these kind of machines. So these are not involute profile forms, so we get from the designer of this pump XY coordinates, read them and put them into our machine, and then dress the wheel and can grind these kind of parts. But this is not the really important point. The important point is to correct these kind of parts in the machine, so we are able to measure the part in the machine or on an external machine. So we have a closed loop in this case, and then move the points automatically to the middle of the tolerance, and then dress the grinding wheel again and do the finishing parts. Correction by hands are here not really possible, because when you have 400 different points to describe the profile form, it's the operator is impossible to correct them by hand. And so this is one of our deep knowledge in this kind of parts, dressing and making corrections at the end of this part. And this is a huge amount of software we are using for this. Also, we have the same things for involute standard gears, external and internal. We can do spline grinding, internal, external, cycloids, whatever you want. We can do on this very flexible machine, and also internal and external grinding. And this is a horizontal machine. And horizontal machine means that the operator is staying in front of all the things he must change during a setup. So it's very nice to set up this machine, because everything is here in this area, and also the control panel you can swivel in, that the operator is staying really next to the panel and can mount these things in the machine.
One question. I see this little tiny workpiece over there. I think, if I'm right, it must be a part of an elbow of a humanoid robot or so.
No, this is a little bit too big for a humanoid robot. Okay. These parts are normally as smaller as you can see in the picture.
Okay.
Here we have a small shaft with a gear with an interference. This will be ground, of course, from solid, because this is module 0.5, something like this. This will be ground from solid.
Anyhow, I see a very small grinding wheel diameter. So what is the maximum RPM you can offer on your grinding
on this machine? The maximum RPM is 40,000 RPMs for an external spindle. So we need these high RPMs for using here these small wheels. And also there's an HSK cone where you can switch the grinding wheel relative easy, because here with these small wheels it's not really possible to dress a lot. And when we are making more parts, as we have done with this part, then we use dressable CBN, that we don't reduce the outside diameter quickly with this wheel. Dressable CBN is only resharpen of the wheel and not breaking out so many cranes as it is here with the ceramic wheel. Right. This works also with internal grinding, as you see in the picture next to this small shaft. There we do internal grinding of a thread in this example here, also dressable CBN wheel. We can do this with internal board screw, with the spline, whatever do you want. We have software here on this machine, so this is absolutely flexible. Maximum diameter is 375, and the maximum length is 870 millimeter. And of course, on the horizontal machine, especially when you do high production, sometimes it took too long to do the meshing and loading and unloading on this machine. And so we have high productive machines for this kind of parts, for worms, for rotors, whatever you want. We can grind on these two spindle machines. So we have a loading and unloading area that you can see in the photo below. Here we put the part in, maybe with a robot. And then we have two NC axes with a meshing sensor, which is driving automatically to the part, checking the run out. There we have a laser where we can see how is the location of the part in the machine, to not to grind too many air, so that the over travel of the grinding wheel is very low. And then we swivel this part into the grinding area, and there we have two possibilities. One is the GW machine with two CBN wheels, as you can see in the picture, one for roughing and one for finishing. And then more flexible machine is GR250 with one dressable machine. So high productive machine with really short idle times, and this makes this machine so productive. Here also an example from rotor and air compressor machine. So in the back on the big photo, you see a big milling machine. This is a CLC 500 HFR with a huge part on this, maximum diameter 500, maximal profile height here is 80 millimeter in one cut. So this is really a heavy machine, close to 40 tons. So really a huge machine with direct drive on the milling head and also direct drive on the table. So this is for really big application, I would say. Also, blower can be cut. Blower has normally 2 or 3 teeth, as you can see in the photo below. This has really huge hobs, length 450, diameter 350, and we cut along this flank line of this blower. So also a good application for this machine. And of course, we have here a lot of possibility to put steady rests in the right position wherever it's needed. And also, of course, we have the possibility to grind these parts on our machine. Here you can see a GW 3600 HD. This is a rotor grinding machine. Maximum diameter of the grinding wheel is 600 and the face width is 260. So also for the blower application, you have here the right grinding wheels on this machine. And these are huge grinding machines which are also able to grind very small parts. And I think this is one of the big solutions. You can grind really from small rotor up to 500 millimeter on one machine. Looks sometimes a little bit crazy, these small rotors on such a huge machine, but it's possible to do. Here, let's jump back to the automotive application. This is a new development from our side. This is a CLC 200HC for hobbing and for chamfering on this machine. So we have here 2 different hobbing heads. One is for the automotive industry, it's up to module 3. And the other one is for industrial application up to module 5. And the maximum diameter we can produce in this machine is 250 millimeter. How does it work? Here we have the possibility to do one cut, and in between we can do the chamfering operation. And the second cut, we remove the small amount of material which is coming out of the chamfering process in lead direction. And this has a big influence on the following honing or generating process. When you have a honing ring and there is some plus material at the chamfer, then you are dressing the honing ring, and this reduces the number of parts between dressing. Of course, and here with the second pass, we cut all these material away, and then we have a really nice flank line. So we increase the number of parts in the following processes. Also here we have one table in the machine and also a tailstock from the top. So also the clamping is very good in this part. Of this part is very good because we have a tailstock, and of course these are all direct-driven motors, the table and the hop head, and we have a big shift range here, so that we can use very long hops to be productive. The changeover time of the workpiece is between 4 and 5 seconds. So also the automation is very fast here on this machine. Can be dry and can be wet, of course. So let's jump to other industrial application. These are the aerospace gears. As I mentioned before, we have different grinding machines, CAG 375, maximum diameter 375, maximum part length 870. Then we have 870 millimeter. Then we have the machines with 500 millimeter diameter up to 2.1 meter. And then we have the GW machines where we are able to grind parts up to a length of 7 meters. So these are really flexible machines. All the machines can be equipped with different grinding heads. Depends on the application we have on this machine. Here, application of an aerospace part. This is a helicopter helicopter double helix gear. So you see a right and a left-hand gear on one part, and there is only a small space in between. That's the reason why we are using here a very small grinding wheel. It's a little bit below 50 millimeter, and this is stressable CBN in this case. Also, this is a direct-driven table, and the nose can be changed easily. Also a very flexible machine. But what is the main point here of this double helix gear? This is the meshing of the part. So you must find a good way to mesh both parts, that you have the same stock on both machines, on both sides of the gear. And of course, we have a cross angle of this right and left hand gear. We call this apex point. So we can mesh this part, and we do this in different position of the workpiece.
Alex, one question.
Yeah.
I see there is an onboard probe on this machine. What can you do with that in detail?
Yeah, we can measure the profile, and we can measure also the lead direction. And this makes it very nice, because we are checking when we are doing the meshing operation, or checking the quality at the end. We are checking this in profile and in flank direction. And then we can say, before we start grinding, we are able to grind this part in a good quality. Because here, when you have a lot of number of teeth, it took a long time to grind this part. Okay. And when you can say at the beginning, this will be a good part, okay, then you save a lot of time at the end. And also the meshing will be done in different areas of this wheel to be sure that we are really have a good run out and all this stuff. So it's an important point to do this before starting grinding here.
So that means by means of this probe, you can make sure that you have enough stock allowance on the whole circumference on the gear, even along the lead, to make sure you have a proper result after grinding.
Yeah, that's correct.
Cool. Okay. Right.
Here another application, it's also a 500 machine. Here we have also a tangential axis in this machine, and we have two spindles which are located in a 90-degree position to each other. One is doing profile grinding. This is the small wheel you can see in the front on the right picture, and below there is a bigger wheel for grinding the OD diameter. Why we are using this? Here the customer, for him it's very important to have a perfect run out between the bearing seats and the gear himself. So with the OD wheel we are grinding the OD seats, and then with the profile wheel we are grinding the gear, of course. And also these are direct drives. Here the small spindle here is 5 kilowatt spindle with 40,000 RPMs, and the other one is a 19 kilowatt spindle with lower RPMs, of course. So also with the probe, we can check everything in the machine. We have a dressing unit also in this machine, and also we can check here on the left picture. You can see this in the left edge. Also, we are checking the outside diameter with the MAPOS measurement probe here directly on the machine, so that each diameter is corresponding to each other, comparison to the quality we want to achieve here in this machine. So let's jump back to the automotive industry. Generating grinding, here we have three different kinds of machines, G160, G250 and G400. And from the G250 we have also a version with the high-speed head, where I come later to this point. Let's look in our G160. This is a machine which can do only generating grinding, and this is a high-speed machine. As Jörg mentioned before, they have a special architecture here. So what is missing in this machine? This is the tangential axis. Also here we are we are calculating or we are interpolating between the X and the y-axis the tangential axis, so that this is a theoretical tangential axis. And what is the advantage of this process? When you see the distance between the spindle blade and the tip of the grinding wheel, this is 100 millimeter less as it is in a conventional head. So the vibration of this machine is less as it is in a conventional machine. So when you look at the end on the surface of the gear himself, the ghost frequency are much lower as it is in a conventional machine. So noise behavior of this gears are much better as it is in a normal machine. What we are doing here on the machine, we are doing here with these small planetary pinions, a two-pass process, a roughing and a finishing process. And what you can see with this special architecture is that the ship-to-ship time here is 1.6 seconds. And this is really fast. Our competitor need maybe 2 or 3 seconds more. And when you see the grinding time here of this part is below 10 seconds. And when you are with the ship-to-ship time 3 seconds faster, this means this machine is in general between 10 and 15% faster as it is on our competitor machine. And this makes this machine so fast, and there is no step against or the risk against burning. This comes only out of the machine architecture, and so this is really a fast machine. All the other things, of course, we have in the machine: acoustic sensor, dressing unit, balancing system, and all this stuff. And what you see also in this machine, there is definitely no cable. So nowhere in cable, it's easy to clean. So this is really a high productive machine. Let's jump back to the bigger machine, G250HS with the high-speed head. We have seen also in the parts before that the number of interference or the part with interference increase. So it's necessary to have flexible machines which can do both generating grinding and profile grinding. Of course, this is here the same as it is in the hobbing process when we can use generating grinding. This is the fastest process comparison to the profile grinding. So when it's possible to do generating grinding, it's a good idea to do this. And you can see this in the picture in the middle. There is a part with an interference. So we are using a very small grinding wheel to do here generating grinding here on this part. But sometimes we have customers who are also interested in a high productive profile grinding application with the two-table concept. We have this here on the machine. These are, for example, customer who are producing gear motors, for example, where they have a pinion a gear pinion directly in the motor. These parts normally also has an interference, and for this you need very, very small grinding wheels, 20 millimeters, something like this. And this you can see in the left picture here. There is a really small grinding wheel mounted on this tool arbor, also with the HSK, so that you are able to do both profile grinding and generating grinding on one machine.
All right, thank you very much, Alex. So we need to speed up a little bit. Now we come to the question and answer session. In the meantime, we have received a couple of questions here. One question is the following. What's the benefit of cylindrical cutters versus the other power skiving cutters? That is the question. Let me explain as follows. In general, there's to say in power skiving, we have two different kind of tools. We have cylindrical tools, or, well, we have this bell shape or tapered tools. The difference is that a tapered tool has already a constructive clearance angle in the tool design. What does that mean? If you want to do a power skiving operation, let's imagine this would be here the power skiving tool. You would cross the two axes in, for example, an angle of 20 degrees, and the contact point would be exactly there where the two symmetry axes of workpiece and tool will meet. Yeah? The machining will happen right there. Okay? In case of having a cylindrical tool, this is not possible. in this case, we need an additional offset, yeah? And this is necessary in order to give the tool its clearance. So we talk about a kinematic clearance angle. Oh. And this offset is required. The main advantage of the cylindrical tools is that we can resharpen them more often because we have a longer profile constants along the width of the tool. And this makes them usually, as far as tool cost is concerned, somewhat more economic. Whereas the tapered tools can be usually designed a little bit more beefy, a little bit more rigid. That's the main difference among the two. Well, do we still have another question here? No time anymore? Okay. So, well, that brings us to the end of our webinar. Whenever you should have further questions with regards to our applications, our machines, gear machining methods, technology, please feel free to contact us either directly or, of course, feel free to make contact to your local EMAG person, your local regional sales manager, or so forth. From our point of view, that's all for now. Thank you very much for joining us today and have a good time. Bye.
Thanks very much. Bye-bye.